Hello, and welcome back to Shiksha DaCosta. Today we're going to learn how to solve real-life problems that involve quadratic relations. So today you're going to be able to look at a situation and learn how to represent it using a quadratic equation, and then how to use that equation to solve a related problem, or even how to use a graph to do that. As part of that, you might need to determine the zeros, you might need to determine the maximum or the minimum, and you may have to do that given a graph or given an equation. To start off, I invite you to pause the video here and see if you can write the equation of this parabola shown in standard form. Well, if you're like me, you would find it very difficult to do that just off the graph. But one thing that I do know how to do is how to find the vertex or the maximum point or the minimum point. And that's right here at -3 and looks like +7. And I also know that if I have one other point, and I can use either of the zeros is a really good point to use here, and I can, of course, find the zeros from the graph just by looking at where it crosses the x-axis. In other words, where does y equal 0? One of those zeros is right here at -4 and 0. And if I have the vertex and one other point, I can use that to come up with the equation of a parabola, not in standard form, but in vertex form. So here, to do that, I just need to find out what is the value of a. So I can replace x with -4, replace y with 0, replace h with -3, and k with 7. And now that I have all of my variables in here, I just have to solve for a. So -4 minus -3 is -1. -1 squared is 1. And now if I just want to isolate a, I can subtract 7 on both sides, and then I'll find out that the value of a, 1 times a is just a, of course. The value of a is -7. And that means I know that the equation of this parabola, not in standard form, but in vertex form, is this right here, -7 times x plus 3 squared plus 7. Now, if you were able to actually find the parabola in standard form, that's wonderful. You can probably skip this next part. But if not, then please pause the video here and see if you can figure out how to turn this into standard form. To do that, all we really have to do is take this and expand and simplify. So the first thing I'm going to look at expanding is these brackets. So here we have x plus 3 being squared, which means really just x plus 3 times itself 2 times. And to multiply two binomials, I sort of use that idea of FOIL, right? I multiply the first two terms, the outer two terms, the inner two terms, and the last two terms, and then I add all of those together. So I would end up with x squared. These two are like terms, so I would get 6x plus 9. And of course, the rest of my equation still has to be here, right? -7 multiplied by all of this, and then plus 7 at the end. Now, to continue to expand, I do have a coefficient in front of these brackets, so I have to use the distributive property. -7x squared, -7 times 6x is -42x, and -7 times 9 is -63. And then I still have that plus 7 at the end, which I can combine with -63 to get -7x squared minus 42x minus 56 as the equation of this parabola in standard form. Now let's look at an example where we may not actually be given an equation or even a graph. Can we still solve a quadratic related problem if that's the case? Here is a situation where we might have to do something like that. So in this situation, a baseball is pitched and Vlad hits it. So it might go, straight over to Vlad here, who makes contact with it, let's say 1 meter high above the ground, because the baseball, of course, is not going to be on the ground. And to hit it, its path is modeled by this diagram. So it's going to go up and come right back down. And that apex, that peak of the arc here, let's say that is 67.5 meters away from Vlad, if we're just going horizontally. And then from that point, if we go straight up, we might go up by 92.125 meters. So that's the highest point that the baseball goes. Now, in order for this to be a home run, it has to go past the fence at the end of the baseball park, right? That fence would be about 130 meters from home plate, and home plate would be right over here. And the fence itself is 15 meters tall. So the baseball has to be above that height when it crosses that distance. Do you think he will score the run here? Or do you think the ball would get lodged in the fence, which might be very, very frustrating for him and any fans of his team? Go ahead and pause the video here and see if you can figure this out and take as long as you like. Well, one thing to note is we can always come up with the equation of a parabola in vertex form if we have the vertex and we have one other point. And this certainly is a parabola-shaped arc. In fact, whenever you throw an object up and it comes down, it'll always form a parabolic arc. And we would start creating that equation just by y equals a times x minus h squared plus k. Now over here, the vertex is h and k, and we can certainly see that that is up here, the very peak, that apex of the arc. And in this case, we might be measuring the x value. The x value here might measure the horizontal distance, whereas the y value might measure the height of the ball when it is that distance away. So certainly we know that h, the horizontal distance at the apex, is 67.5 meters. We know that already. And we know that the ball is also 92.125 meters high, and that's k. But what about x and y? Do we have one other point on this arc? Certainly we know where the ball starts, right? At the point of contact when he swings and hits the ball right here, it's 1 meters above the ground, and that's our y value. But what is our x value at that point? What is the horizontal distance the ball has traveled? Well, I think if you really think about this, you'd be able to figure out that it must be 0, right? As soon as he hits the ball, it hasn't traveled any distance horizontally, even though it's 1 meters high. The 1 meter high is sort of where the ball was pitched to Vlad. So now that we have an x and a y, an h and a k, we can substitute those values into our equation right here and solve for a. So 0 minus 67.5, of course, is negative 67.5. And now if we start to try to, if we square this, we'll get 4,556.25. And now if we start to isolate for a, let's subtract 92.125 on both sides. And now let's divide both sides by the coefficient here. And that would isolate a. And we'd find out that a is exactly negative 0.02. So the whole reason I did this is it would be really, really helpful for me to have an equation for this arc, because now that I have this equation, and this is the one that I came up with, h might represent the height of the ball when it's d meters from the home plate. So that equation right here tells me exactly how high the ball is, depending on how far we're measuring from home plate. And I can use this equation to find out, is the ball going to be over the fence when it reaches the end of the ballpark? Of course, to find that out, the horizontal distance the ball has to travel is 130 meters. When it does that, when it travels the full 130 meters, I have to find out how high the ball actually is above the ground. And I can do that just by plugging 130 into d. That is the d value when the ball is at the edge. And if you were to put this into your calculator and evaluate it, you would get exactly 14. Oh, so close. So what this means is the ball is 14 meters high at this point, which means it's not going to go over the fence. It's going to hit right below the top of the fence there and fall to the ground. So you can actually use the graph of a quadratic to come up with its equation, or if you're given the equation itself, that'd be pretty ideal. Either way, the equation is super useful because you can use it to solve the any further problems that result from the situation in a way that's exactly accurate. If you are able to come up with the equation in factored or vertex form, you can always turn it into standard form just by expanding and simplifying. And the reason you might do that is because standard form is really, really useful because we can solve every quadratic generally like this. And to find the zeros of a quadratic in standard form, you may remember how to use the quadratic formula. You can also use a factoring strategy, but sometimes that might take you a little bit longer. Not every quadratic actually is factorable, but certainly the quadratic formula can be used for every single one to find the zeros. Standard form is also useful in obtaining the vertex. The vertex is always going to be at the h value is always going to be negative b over 2a, and the k value is always going to be c minus b over 4a squared. And this right here would always represent, because it's the y value of the vertex, it would always represent the maximum or minimum. Now, when you're working with real life problems, it's always good form, whether it's quadratic relations or not, to define your variables. As soon as you start creating a problem and as soon as you introduce a variable, write down what that variable is supposed to represent. What quantity are you measuring with it, including what unit are you using to measure that quantity, whether that's meters or seconds or anything like that. When you're done solving the problem, you definitely also need to include a final statement to summarize everything that you've learned or whatever your solution is in a way that is clear and concise. And in doing so, you might realize that one of the things that you have written down doesn't really make sense. So, in some cases, in quadratic relations, a solution might not be admissible. It might not actually make sense. For example, if you're trying to track time, and you solve it using the quadratic formula and you get a negative number, well, I guess in some cases time can be measured backwards, but most of the time when we're measuring something, we always measure time in a positive manner. How many seconds maybe have elapsed since we started measuring? If you get a negative number, you may have to disallow that. And every situation is different. So every situation may have different reasons for you to disallow a solution. Please make sure that if you are disallowing something, you're always writing down the reasons you're doing that. Let's say we have a bus company that has 17,000 passengers a day, and each passenger pays $3. Now, the bus company always obviously wants to maximize its revenue, so they decide to increase the fare. And every time they do that, every time they increase the fare by 25 cents, the company estimates that about 850 passengers will say, "That's too expensive for me," and choose an alternative way to get to work. So the question that I have for you here is, what fare would actually maximize the daily revenue? What should the company charge to get the maximum amount of money? And what is that maximum? And what fare would result in the company actually making no money? Pause the video here and see if you can figure out the answers to any of these questions. Well, if we're trying to maximize the daily revenue, we have to find out how do we actually calculate revenue. And the revenue is the amount of money that the company is making. And obviously, if we have 17,000 passengers, each paying $3, 17,000 times $3 would give you the total revenue that they're making right now. To put it in a shorter way, the revenue that this company is making is always the fare they charge multiplied by the number of passengers that are paying that fare. And if I want to create an equation out of this, let's define some variables as we start. So I'll say let R represent the revenue, and the revenue depends on something. The revenue is the dependent variable, and the thing that it depends on is the increases of the fare, or how much the fare actually is. So I'm going to say if they increase the fare once, they lose 850 passengers, and once is increasing it by 25 cents. If they increase it 2 times, they will lose 1,700 passengers. And so the revenue depends on the number of price increases. So I might put a statement like, let R represent the revenue after X price increases. The fare is pretty easily calculated. If we're increasing the price X times, the fare starts at $3. And every time we increase the price, we're adding 25 cents. So we're taking $3 plus 0.25 times X price increases. And the number of passengers starts at 17,000, but it actually goes down. It reduces by 850 again every time they increase the fare. So it might be something like 17,000 minus 850 times x. And both of these equations depend on the singular variable x, the number of price increases. If you haven't been able to make much headway in this problem, here's a good chance for you to pause and see if you can figure out the rest of it from here. Well, if the revenue is the fare times the number of passengers, we can and R is the variable we're using for that, well, we can represent the revenue with this equation. 3 plus 0.25x is the fare times the number of passengers, 17,000 minus 850x. And to find out the maximum daily revenue, one way I can do that is to find the vertex. And there's many, many ways to do that. Today, I'm going to be doing it a very specific way that involves standard form, because I really want to show off how powerful standard form is. To get to standard form, of course, I have to expand and simplify. And to multiply these two binomials, I multiply every term in the first one by every term in the second. So 3 times 17,000, 3 times negative 850x, then 0.25x times 17,000, and 0.25x times 850. Of course, these two are the like terms here. So when I add all of these up, I'll get the revenue is equal to negative 212.5x squared, right? That is the only x squared term that I have. And as I combine my two like terms, I'll get 1700x plus my constant 51,000. And notice I reorganized my terms in descending order by degree. So this is x squared, x to the power of 1, and my constant, of course, at the end. Now that we've got the equation in standard form, we can use this to find out what fare maximizes the daily revenue. And using the formula for finding the vertex very easily from standard form, that those 2 points right there, all we have to do is substitute in B, A, and C everywhere we see it here. And I'm just going to do that right now. After you evaluate this, you should end up getting 4. And if you evaluate this part, you should get 54,400. So what this means is that when x is 4, so after 4 price increases, the revenue is $54,400. So 4 price increases actually maximize the revenue, and that would be a fare of $4. And I got that just by taking my equation to calculate the fare and inserting the number of price increases, which is 4, and evaluating that. This also tells me the maximum revenue, like I mentioned, is 54,400. So those two questions I have fully answered. When it comes to calculating the fare that results in the company making absolutely no money, well, for that to happen, the revenue would have to be $0. So I'm just going to replace R with 0. And now I can, to find the zeros of any quadratic relation, all I have to do is use the quadratic formula. So I'm going to replace B, A, and C with what they're equivalent, what they're equal to over here. And now I'm going to start to evaluate this. So this is just negative 1700. Everything under the square root, if I put that into my calculator all at once, the discriminant is a positive number. So I know I'm going to end up with 2 solutions because the square root of a number should be, there are always 2, a positive and a negative that result in that, or that result from that, excuse me. And once I do actually square root this, I'll get 6,800. And so at this point, I would split up my quadratic formula into these 2 different solutions. This one, as I evaluate it, I'll get negative 12. And as I evaluate this one, I'll get 20. So what this means is one of the solutions is negative 12 price increases. And the other one is 20 price increases. Is negative 12 an admissible solution in this case? Actually, yeah, a negative price increase would actually be a price decrease. And it might actually be better for the company to lower their prices in some cases. In this case, no. 12 price decreases result in a fare, if I change x to negative 12, will result in a fare of, well, $0. And of course, no matter how many passengers they get, if those passengers are coming on for free, the company's not going to make any money. So that makes sense. If I increase the price 20 times, that would be like charging a fare of $7. And if I increase the price 20 times, yeah, if everybody's paying $7, that's wonderful. But 850 passengers have chosen an alternative commute, and that's happened 20 times. And 20 times 850 actually is 17,000. So even though my fare is $7, I have no passengers, and no one paying $7 still gives me a total revenue of zero. So both these solutions are admissible. A toy rocket is launched from a table, like you might see over here, and its height in meters is given by this equation, where t is the time elapsed since it was launched in seconds, and it's actually supposed to deploy a parachute when it falls to 10 meters. When would this actually happen to the nearest tenth of a second? So here we have two variables, right? H, which is the height in meters, and T is the time in seconds. See if you can figure out when that happens. Pause the video here and take as long as you need. Well, if my equation here is 10 equals, right, the height is 10 meters, I'm trying to find out what value of t makes this true. But unfortunately, I can't solve a quadratic equation if one side is not equal to 0 and this side is equal to 10. But it's pretty easy for me to fix that. All I have to do is subtract 10 on both sides, and that would reduce the left side to 0 while changing the quadratic on the right by sort of shifting the parabola down by 10 units. And that only just changes the constant here, right? 2 minus 10 is negative 8. Now that I have this here, I'm not even going to try and factor this because decimals, ew, I don't want to factor something that involves decimals. So instead, I'm going to use the quadratic formula. I'm going to plug in all my values for A, B, and C into here, and then evaluate. So here I have negative 15. If I evaluate the discriminant, I get 68.2, and 2 times negative 4.9 is negative 9.8. And this, of course, is going to split up into two different solutions, the positive and the negative. The negative, if I evaluate this, I end up getting about 2.37. And there's many, many more decimals after here because this is an irrational number. And for the version where I'm adding the square root, I get 0.68 ... which indicates there's many more decimals there too. Now, between the two of these, are they admissible? Pause the video here and think about whether or not we can use either one or both or even neither as a solution. Well, hopefully you realize that, well, if this is the parabola, or this is the equation that creates the parabola of the rocket going up and coming down, the a value being negative means that the parabola is shaped, is opening downwards. And that means that these two values give me the time that the height is 10 meters, and that will happen twice. It'll actually happen once going up and once coming down. And I'm trying to find out when is the parachute going to deploy, and that happens only when it falls to 10 meters. And so here we can see that the parabola might be shaped something like this because it's opening downwards. As it's going up, it crosses the 10-meter height mark at about 0.68 seconds. And then it comes down and it passes it again at about 2.37 seconds. And so 0.68 would actually be an inadmissible solution, right? We don't care. The parachute is not going to deploy on the way up. It's going to deploy over here when the rocket is falling down. And so my final answer here would be the rocket would deploy its parachute at about 2.4 seconds because I'm rounding that to the nearest tenth. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.